I'm Alex Herzig. I'm a geospatial modeler here at Temporal, based here in Palmerston North. And I started a tag team presentation with my co-authors, John and Anna. We're going to talk about the modeling bit and the development and where we're at the moment. So I'll briefly outline the concept and then talk about the erosion model. So it's a two component model about the implementation calibration. Aman's going to talk about the sediment transport component. And John is going to talk about conclusion, little summary, and he's taking all the questions. So the motivation, I guess, should be clear by now. You've all heard a lot of it. Just to sum it up, sediment quantity and quality affects ecological integrity of rivers. And the objective of this work and the model is to predict sediment concentration in rivers at low flow. The basic concept is that we've got two basic components. One component is looking at the brown arrows here. So that's the contribution from the land. So that's the erosion and the erosion processes. Or my previous colleagues from Monarchy Fenway have talked about. And the second component is the sediment transport model that looks at how the sediment that goes into the river is transported into the river, along the river, and into the receiving environments. This is a high-level outline of the concept. So we've got those different components, the erosion model on the left-hand side, river transport model on the right-hand side. On the erosion model side, we're looking at our traditional erosion processes. And specifically in this model, we're looking at rainfall-driven soil water budget and how it drives soil erosion. Then we sum it up, those different processes at the Rec 2 catchment, and then we produce a load that together with river flow will be turned into a concentration. And Simon's work and Hugh's work contribute to the sediment quality part of it. So there's a breakdown in terms of particle size. So this is some more detailed concept of the model. In the middle, for the hill slope and erosion model component, very important, the soil water budget, which drives basically all the components. That's rainfall driven. We get rainfall from a satellite. That's in a 3-hour interval, and that's the modeling time step of our model. And then it drives various processes, obviously, or affects various processes in strength terms in the soil. For example, it creates overland flow, and the depth basically creates a force on the soil that determines how much is eroded via superficial erosion. Similar for gully erosion. And the other two processes, landslide and earth flow, basically driven by the competition of pore water pressure and the cohesion of the soil, so the ability to stick together, and that's obviously dependent on the water content. So we're modeling those components of those processes, and then derive the soil erosion for the individual processes. We create a sediment load, and then we hand it over to Amar. In order to process all the soil physics and also then some of the soil erosion, we've implemented an interoperable modeling framework, which allows us to use the high-performance computing infrastructure provided through NESI. So the soil physics is computed in a sequential way. And so we're extracting rainfall, calculate the soil water budget, and very important, the depths of the saturated soil water in the soil profile, as well as the excess drainage, that's the overland flow. And those two terms basically control those four processes. And once we've done the sequential computation for scenario modeling, we can actually do it in parallel because we've got physics and we can change land cover and use the same calculations and then derive our erosion terms from that. We've calibrated the erosion component using our sediment model in that way that the sum of the erosion that's produced by this temporally disaggregated model sort of matches the mean annual erosion yield or loads from the sediment model. So we've got sort of like a temporal component here where for each of those time steps in a year, so we've got 3-hour intervals, so it's around 3,000 time steps. So this temporal component is summed up for each pixel, and then all the pixels are summed up for each Rec2 catchment, and that's then the value we hand over to Aman. We do that for all of those 13,232 catchments, Rec2 units in the Manawatu catchment. And sort of to make our modeling work and meet those mean annual average yields, we've used those sort of parameters to calibrate the model. So that's the cohesion for landslide and sort of like a constant term that's sort of working with the effective stress on the surface, the speed of gullies and of earth flows, and the density of gullies. In the next sequence, just sort of to give you a bit of an idea of how the model works. So we've got 3 sort of time steps, or it's one time step, 3 different processes. So precipitation on the far left, then the soil saturation in the middle, and then the erosion on the right-hand side for the same time step. And just to give you an idea how that looks like, we can see that there's a little bit of precipitation already here. We've got some soil saturation already here. That's the depth of saturated soil water. And we can't see any erosion as yet, but it gets more colorful. So we see precipitation sort of moving into the catchment, the soil sort of more saturated, and we've got sort of a tiny bit of erosion. That's total erosion combining all the progresses. We see this getting a bit stronger. We've got a little bit more precipitation here, saturation increases and spatial coverage as well. And we see, again, a little bit of erosion. Here, oh, by the way, this is so the dark red bits are sort of 25 millimeter and beyond in terms of rainfall. And this is sort of 100 millimeter sort of set. The dark red is beyond 100 millimeter saturated soil water. And so we see here that a large area of the catchment is saturated, and it leads sort of to the erosion we see on the right-hand side. And we see as the sort of fronts moving through the catchment, sort of saturation is clearing up a little bit, and we see more erosion on in this area of the catchment. And now I hand over to Aman to talk about the sediment transport model.
Hello everyone, Arman Hadrachi from Viva, Christchurch. So I will briefly talk about the river part of the model, sediment transport. Basically what we are doing is this event scale model that we are developing. We get all the sediment data from land care up to the river, and then we will put it into the river and transport it downstream. So the river model is the routing model. It's like we are using the erosion and sedimentation to route the sediment down the river network, and we link the eroded materials from the sources to the sinks in the either it is ocean or lake or whatever, or maybe monitoring site of the river network. Remember that it is a bonding model, which means that it is a depth average sediment concentration. We don't have changes in the depth of the water, and it is a cross-section average. We don't have variability of sediment concentration within the cross-section. It's just one value for one reach of the river. And again, so it's bonding model. Yeah, the routing model has geomorphic processes, including the, as I said, deposition and re-entrainment of the sediment for each reach of the river. And we can see how much deposition we have at each time step and how much erosion we have. Another geomorphic process considered on the model is the connectivity of the river networks. Basically, wherever we have any disconnectivity from the lakes, natural lakes, or dams, it should be stopped. And we have some sort of settling coefficient to calculate what is the input, what is the output. We also have the impact of particle size, which I talk about that. However, the model needs a hydrological model on top of that to force the sediment down. For that purpose, we use the TopNet model, NIVA hydrological model, to force as the force of the flow during the flood. So we have the flow data, model flow data for every 3 hours, and then we disintegrate it to 1 hour to use it in the modeling work. So impact of the particle size, the test river model, as I said, can independently model each fraction, which is the beauty of the model. So we can have any fractions that you need for modeling, 10 fractions or more. And for sediment concentration, we can divide it to any of the fractions that we have and then model that separately and then sum them together. And route the sediment down the river network using these different fractions. We can also calculate the deposition and reentrainment of the sediment for each reach segment of the river. For each fraction. Basically, we can say how much sand is deposited in this reach, how much silt, how much clay is there, and then doing that for all the catchment at each time step. And we can sum them up to see the rate of the deposition. For our work, we selected 4 size classes. Again, as I said, in the model, there is a capability to select more sizes or less sizes. But for the modeling that we do in the Manavati, which I show you later, we selected 4 fractions. And the model has some inputs, flow data, which is coming from the TopNet model that we are using, and sediment data, which is sediment concentration, or sediment load and particle size, coming from the Alex and John's model for the upper catchment for erosion sources. And for in-river flow data, we again use the flow data from TopNet model to run. In addition to the flow and sediment concentration data, we need for the model run some characteristics such as riverbed slope, length of the river reach, and connectivity. And the output of the model would be sediment concentration and each reach of the river for different times. So these are the time frames. And particle size. Basically, we are running, as I said, the model separately for each fraction. That's it. In addition to that, we can calculate the load of the sediment for each event, which is basically by multiplying flow data and sediment concentration data at each time step, and then calculating the load in kilogram per second. And if you sum them all together, you can get the load, event load for your calculation. By using a submodel for visual clarity, we can calculate visual clarity at each time step for the model. So basically, if you have sediment concentration data, you can have same graph for which is opposite for the visual clarity using a submodel for each reach of the interval. I don't want to go through the details of the model. I got PTSD by running this model. It's really hard to do that. 5 years of like non-stop work on that one. I mean, not non-stop, but yeah, a lot of discussions and with John and with Chris pushing us very hard. But yeah, I think we are getting there. So briefly talking about the model, it is the mass conservation model. It has the elements of the depth, unit flow as the input of the model, and erosion and deposition, which you can see the change or the change in the mass on each reach. and then you have the dispersion coefficient in the model. So basically, when sediment is transporting downstream, in addition to deposition, it will disperse when it goes down. So, and again, it has the time steps and distance steps that we can run it. And basically, what we are doing is trying to calibrate the model in a catchment, which I'll show what is that, by calibrating some parameters, some calibration parameters in erosion and deposition and dispersion term in there. And as I said, it has different fractions. So we run this mass conservation for each fraction separately at each reach, and then sum them together to calculate the total concentration. So to test the model, we first tested as a stationary state, basically removed the distance from the model and just run it in Oreti River data for one study site to see how the model is working or how the conceptual model frameworks work by calibrating the load data in the model. And we found that the model was very strong in calculating load as the stationary. The results published in WRL last year, conceptual framework. Now what we are working is trying to expand the model into the state, basically running the model through the river network. We used the Crank-Nicholson scheme for those who are interested, and came up with like a learning technique or time learning technique to run the models. And for calibration, we are calibrating the model in Manawatu River catchment using 2 upstream size as the boundary condition of the model by comparing the results in the Manawatu for a couple of flood events from 2017 floods to 2019, selecting around 5 to 6 events for model calibration and 3 to 4 events for validation of the model. Again, upstream size are the boundary condition of the model, so we use them as the input data. Flow data is coming from the topnet model, and we compare the results of the model versus the measurements in Manawatu data. We have high frequency data in all these 3 sites. And this is one of the events that I'm at the moment working to calculate the load or sediment concentration or visual clarity. You have the 2 upstream size that makes the flow data and sediment concentration. Sediment concentration is the dashed lines, and downstream side is the TCOL that we want to see if the model is coming to some extent agreement with the load calculation of the Teachers College flow data. In summary, high frequency sediment data are necessary for designing sediment management, and of course, not all of the councils can do the measurement in all the rivers, so you need the model to do that. And this model, when completed, can help to address the main questions. There are 3 main parameters that needs to be measured in river, which is sediment concentration, sediment deposition, and visual clarity. And this model that we are developing provide the attributes for all these, or the measurement for all these 3 attributes by direct measurement of sediment concentration, direct measurement of fine sediment deposition, and indirect measurement of visual clarity by making sub-model. I will hand over to John.
It's very complex.
You'll make it so. You'll make it so.
It is a very challenging model to get going, and very privileged to be able to work with NIWA on this. So what I probably haven't emphasised is the temporal model, and so we need to get at the model of sediment concentration in the rivers as a function of time. The most important reason for this is that in managing water clarity targets, they are basically set at median flows, really a low flow. So most of the sediment has gone downriver well before the median flow. So how do we relate soil conservation efforts to these targets of visual clarity. And to do that, we need a temporal model. So at the moment, we make this assumption that if you reduce sediment loads by, say, 50% by soil conservation, that will reduce your sediment concentration, low flow by 50% also. We don't know whether that's true or not. But we've been making these assumptions for a while. I think you probably make those assumptions in your work of the economic analysis as well. And not only is that not necessarily true, but the quality of the sediment also changes. So if you might make a reduction of 50% of the sediment load, but it's assuming that the particle size is the same at medium flow. We don't know whether that's true. But that's the reason why we have to get this temporal model to look at that. And that'd be one of the first things we check. We run some scenarios with soil conservation scenarios and just see what happens to that sediment concentration at medium flow. So the main question.
Here are some take home. Next slide. Take home.
Okay, take home messages. And I was really talking about the last one there. Check about the impact of soil conservation on the visual clarity and low flow. I have a feeling it's not going to be quite as good as what we assume. Those fine particles affect the visual clarity more than